So now let's start our first session, and Liang Fu will be the chair.
All right. So we are very honored to have a distinguished speaker, Allan MacDonald, give the opening talk. Please.
Thank you.
You can keep it.
Is it coming through? Yeah. Okay, so I must say it's a great pleasure to be on this campus. I'm from Nova Scotia, which is up at the end of I-95 and then 400 miles beyond. So I've driven past this place on I-95 100 times in my life. And so I'm glad I finally had the chance to come in here, see this beautiful campus, and to learn that it has my kind of science going on. Okay, so I've been asked to give a tutorial talk. I'm going to talk about manipulating, about how we describe the manipulation of electronic states in 2D materials with Mories patterns. Mories patterns, as you probably know, happen when, whenever you have two similar periodic structures, and the spatial beating pattern makes a longer periodicity. That's the Mories pattern. The Mories patterns we're interested in here are overlaid 2D crystals. Whoops, maybe that's not going to work. I got lost on my way here. I'm not sure how many visitors got lost trying to find this room, but I didn't get time to get my pointer properly organized. So I'll just point. So there you have a blue 2D crystal, a 2D crystal square lattice marked by blue links, and another one that's rotated but has the same lattice constant marked by red links. And you can see with your eye that, that there is a long period structure in which the stacking between the two layers slowly varies. Okay? And so it turns out, as I will talk about, that the electronic properties in some 2D materials, the electronic structure when you have a Mories pattern is described by an emergent periodic Hamiltonian that has the periodicity of the Mories pattern. So it acts like a giant crystal with a lattice constant that we can control simply by varying the whoops, thank you. Okay, by varying the rotation angle, and which is experimentally typically, on around the 10 nanometer region. So this is one example among a number you could point to of ways in which we are now realizing, actually, as you'll learn during this meeting, if you're not in this subject yet, which we can have great success in controlling the properties of materials by controlling the placement of atoms on an atomic scale. In this case, that control is only in the overlay direction. So we're along one axis, at least, we're realizing this vision articulated by Richard Feynman more than 60 years ago. Okay? So the most important thing about these artificial periodic structures is that the period is long, much larger than atomic, but not too long. Okay? So when we have a layered electronic system, we know that we can make it part of a capacitor, make an electrical gate, in other words, and vary the electron density. So when you think about the physical limits of that, it's clear that you can't change the number of electrons using a gate by an amount that's comparable to 1 electron per atom, because then you'd be changing all the chemistry and the material would just fall apart. So it turns out the physical limit in a field effect transistor, as this is called, is that you can change the number of electrons by by about 1 electron, let's say, per 1,000 atoms or so. That's the most you can do. And but in these artificial periodic systems, the Mories materials, the size of the unit cell, the artificial lattice constant, is typically about 100 times larger. Unit cell areas 10 to the 4 times larger. So that means that we can change the number of electrons per artificial atom by typically maybe around 10 or so. And that means that we can, in effect, in this, these different worlds that we make, different periodic tables, we can move through the periodic table. Moving to the right in the periodic table, of course, is increasing the number of electrons per atom by 1. So we can do that in these worlds. Okay. Second thing that's important is, and which I will talk about in great detail, or at least a lot of detail, is that this trick of making an artificial periodic Hamiltonian only works if the starting material is either a semiconductor or a semi-metal. The reason that's important is, I'm showing here the materials that I will talk about mainly: graphene, honeycomb lattice of carbon atoms, and transition metal dichalcogenides, of which tungsten diselenide is one example. And as you can see in this green circle I've marked here in the graphene case, because this is a semi-metal, or strictly speaking a gapless semiconductor in this case, all the low energy states are close together in momentum space. And the qualitative physical thing is, if you've got a bunch of waves that have similar wave vectors, they can't resolve spatial structure on a length scale smaller than 1 over the size of this circle. Okay, so that's the reason why in these materials it turns out that these Mories formed from 2-dimensional crystals are actually not crystals. They're not strictly periodic. Only the Mories pattern is periodic, but over a limited energy range, usually the energy range of interest, the electrons only see the Mories pattern. Okay, so that's the reason you can make an artificial crystal, and it wouldn't work if you had a 2-dimensional metal, for example, like niobium diselenide. Okay. Another thing that I'll mention as I go along is a little bit anyway, is topology. And so if I go back to graphene, you can see here that at each momentum there are 2 states. And it turns out that that at these high symmetry Brouin zone corner momenta, like K, there's a double degeneracy. So there are 2 degenerate states at each momentum, and they're nearly degenerate at nearby momentum. And so when you make a Mories pattern, you disturb the pattern of those states in momentum space. And because you have these 2 nearly degenerate states, the block state will end up depending a lot on momentum. And that gives rise, that 2-level system is the simplest example system for talking about Berry phases. And we know that a 2-level system state can be mapped to a direction on a block sphere. And if you go around paths, for example, paths in momentum space that enclose area on this block sphere, then you get a Berry phase. Okay? And so the degeneracy of the states, or quasi-degeneracy of the states, makes it very easy to create topologically interesting states. And okay. So that's for, for graphene mores. And so for graphene mores, we knew before we started this subject that Berry phases and associated things that I'll mention, like that a quantum anomalous Hall effect would be part of the physics. What's been a big surprise is that in the TMDs, that's also true for reasons that maybe weren't so obvious at the beginning. Okay, so that's the overview. There's actually no clock in this room. I was told to take 40 minutes and leave time for discussion. I can't actually, I know from experience, I can't say very much in 40 minutes, but I will stop after 40 minutes and I'll be here. Please don't hesitate to interrupt me, and anything you're interested in chatting about, we can do it during the breaks. Okay, so now I'm going to go really slow and talk about what the models of what the periodic Hamiltonians I was referring to before look like. Here I've shown a one-dimensional crystal, a red crystal, like on my slide. Here's a blue crystal. So this is a two-layer system. If I, if I make a Moire pattern here, which I could do with one-dimensional crystals if they had slightly different lattice constants, then locally what's happening is the position of one layer is moving relative to the other. And so let me just make one more point here. So actually, a blue electron can tunnel to the red layer. It doesn't tunnel just to the closest atom. It tunnels to a bunch of atoms nearby. And but the range over which the electron, the dominant tunneling processes occur, is atomic scale, maybe a few lattice constants, whereas the period of the Moire is much, much longer than atomic scale. And that means that on the Moire scale, this tunneling from layer to layer is practically a local function. You tunnel from one position in the Moire pattern to the same position in the Moire pattern. And so here's one way of making a model of a Moire system. Let's say I have two weakly coupled layers, and I know that the dominant physical process by which the layers interact with them is that electrons can tunnel from layer to layer. That's the case, for example, for carbon, because carbon atoms are neutral. They don't make an electric potential in the other layer. This tunneling I was talking about here, a local function of position, should be, if, as I did a moment ago, if I vary the stacking so that I've moved basically by one lattice constant. So I'm letting this vector d here represent the stacking between the layers. And if I change the stacking by one lattice constant of this one-dimensional crystal, I've returned to the same physical state. So I should have the same Hamiltonian. I should have the same hopping parameter. And but actually, if I'm keeping track of these atoms one by one, for example, in the case of carbon, the bands near the Fermi level are carbon pi orbitals. And so if I'm keeping track continuously as a function of d of all the carbon orbitals, then, and I'm interested in a particular wave vector here that I've called big K. Big K in a moment will be this Brouin zone corner wave vector. And then the layers have moved from relative to each other by a lattice constant. So the block wave that I make that has wave vector k will change its phase on the site directly above a reference point in the blue layer, for example, by a. So I get an extra phase factor. So the hopping is essentially periodic, but I can take account of this little phase factor. And, so if a function of d has this kind of periodicity, we know periodic functions can be expanded in terms do Fourier expansion that involves reciprocal lattice vectors in a crystal. And so here the expansion vectors are reciprocal lattice vectors plus the wave vector of the block wave I'm interested in. Okay? And the wave vector I'm interested in is a wave vector at the center of the region of momentum that contains the low energy states that I'm interested in. So if I was interested in a term in the Hamiltonian, as I'll talk about in a moment, that is within a layer, I wouldn't get this extra phase factor. But if I apply that, sort of recipe to graphene, so I say the orbitals are pi orbitals. A pi orbital can hop to the other layer in some region around that starting point, but that's smaller, much smaller than the Mories period, then it's basically local tunneling. And I know that it has a Fourier expansion that are reciprocal lattice vectors here for a honeycomb lattice, a triangular reciprocal lattice. The black vectors here are a sketch of reciprocal lattice vectors, and the red ones are displaced by a wave vector that is on the corner of this Brouin zone that I've marked in green. You remember from solid state physics class that Brouin zone is constructed by putting lines along by intersecting the lines that are halfway between the origin and the closest reciprocal lattice vector. So this is the reciprocal lattice vector, slightly imperfectly drawn, and these turns out that the three smallest Fourier components that appear in this expansion are these three red ones here that have the same magnitude. And so if I argue that these two layers, it turns out in these Mories systems, or in these two-dimensional materials that are van der Waals materials, the layers are always further apart than the lattice constant within the layer because there's weak chemical bonding between layers, and mainly van der Waals bonding. And, and so that means that when I look from the other layer, the rapid variations in the layer that's far away tend to get washed out. And so there's a motivation for thinking that this tunneling function will be a smooth function on the Mories scale. And we can take the smallest magnitude Fourier wave vectors. And so that, this is a type of pitch argument. If you kind of understand the electronic structure, as we do for graphene, we can just sort of guess what the Hamiltonian might be. If you apply symmetry, it turns out that the three Fourier coefficients for these three spatial modulations of the tunneling, components of the spatial modulation I've indicated here, that they all have, by symmetry, they're all connected, and there's only one real number that characterizes the tunneling.
I'm sorry, Allan.
Yeah.
So this is a local construction, right?
Yeah.
And this construction would be different in different parts of the Mories.
Sure.
So this is a local construction.
I can repeat it if we can't make it. Okay. Yeah.
Okay, so the question is that this is a local construction, right? Somewhere in the Moray pattern.
Yeah.
And if you go to another place in the Moray pattern, let's say the environment, the local environment is going to look different.
Yeah.
So then, in analogy with, let's say, long-range ordered crystals, when we construct the Brillouin zone, we're not worried about where we are making the construction. But here, it seems that this construction is kind of local. And if I go to some other place,
The tunneling, so the tunneling between the pi orbitals, if you think about it on the Moray scale, it's local. It's a function of position, as you were saying. And it has a Fourier expansion. And if it's smooth, only these three coefficients matter. These three different directions are, related by 120-degree rotations. So it won't surprise you that if you work through the symmetries constrain these Fourier coefficients to be equal. And so the spatial variation of, as you say, it is spatial dependent. The local interlayer tunneling between pi orbitals is described by one number. Okay? Yeah. And so that one number describes in that, in this smooth argument, you can reduce it to one number, describes the dependence of the Hamiltonian locally on stacking. And if I have this twist-type Moray pattern that's produced by rotation, then it turns out the displacement is, for a rigid rotation, by small angle would be linear in coordinate. The displacement modulo reciprocal lattice vector, the displacement modulo lattice vector is periodic. It has the periodicity of the Moray pattern. And so since D is linearly related to R, that means a Hamiltonian as a function of D, a correction to the Hamiltonian due to interlayer tunneling, that's a function of stacking, turns into a correction to the Hamiltonian that's a function of position. And you can elaborate this, I won't talk about this in any detail, to take account of the fact that, even for any twist, there's always some strain relaxation because the energy depends on stacking, so there's always some force that acts. Basically, if I think about the graphene example, this adds to the Hamiltonian due to the interlayer coupling, a term that is calculated for a particular momentum in the Brillouin zone that depends on position. And I think I have a slide out of logical order here. So I'm going to make another point in a moment, but let me just say this. So if you take that argument, you get interlayer tunneling between the carbon atoms. Carbon atoms, of course, are arranged on a honeycomb lattice. So there's A and B sublattices in each layer. And this is just looking at an example, the complex number that describes the local tunneling between a particular sublattice of one layer, a particular sublattice of another layer. And it's some function of position that's described by one number. Okay? And so I've skipped over something I'll come back to in a moment, but it turns out, this was a surprise to us, not something we understood before, that if you take this kind of model building, which ends up giving you periodic Hamiltonians with the periodicity of the Moray pattern, if you go to large twist angles, when you tunnel between layers, you change momentum. If you have a large twist angle, that means the Moray period is short, you change momentum by a lot. And in graphene, low energy states are present only in a small region of momentum space. So basically, when you go to large twist angles, coupling between the layers doesn't matter. Okay? As you go to smaller and smaller twist angles, the the strength of this tunneling between the layers, which turns out to be on the order of 100 millielectron volts, becomes more comparable to the change in energy within each layer when you get from the momentum boost. And when they become comparable, the layers become strongly coupled. And it turns out that just numerically, and this is partially from so-called chiral models, many of you know, understood analytically, it turns out that instead of just becoming the bands, you might guess that when the two layers get coupled, the electrons will slow down. And as they get stronger and stronger coupled, a good guess might be they get slower and slower. But it turns out that there are a discrete set of twist angles, so-called magic angles, where the bands, that the electron velocity, so this is energy as a function of momentum in the momentum space of the Mories pattern. And so derivative of energy with momentum is velocity. So this is a narrow band. There are actually 8 states here for each momentum. And the velocity of each of these states is typically sort of about a kilometer a second. Okay, so this is slow electrons, not slow light, but I think you can make light even slower, but this is slow electrons. In ideal models, you could make the electron velocity 0. So it turns out you can have many states that have almost the same energy in this system. And we always know in condensed matter physics that when you have so-called flat bands like this, then interactions become very important. So this is an example of a way that you can make strongly correlated electron states. And of course, as we'll hear in the tutorial tomorrow, techniques for actually taking layers and having well-controlled twists are by this time very well developed. So for twisted graphene and many other systems, one is able to study the electronic properties of systems in which these 8 states per Mories period that appear in these bands are partially occupied. And and often, one of the things that gives rise to interesting electronic behavior is having the kinetic energy be less dominant, having the velocities be small. So this had been great fun for basic physics if one in the fullness of time develops applications based on these artificial periodic systems. It might be that in that case, what we want is wider bands. But here was a great accident that these are narrow bands. Okay, and okay, whew. Okay. So I showed you a Hamiltonian with a block periodicity. And so this Hamiltonian has this correction term I was talking about, which is local in space. But we have to include the k-dependence of the Hamiltonian that we originally had. And so, one practical recipe for doing that is just include the k-dependence at some representative stacking and include the stacking dependence at one momentum. This, in the applications of interest, this stacking correction is small. It has a k-dependence on the scale of the atomic lattice constant. We're only interested in k-dependence on a much smaller length scale. So we can neglect the k-dependence of this Mories stacking dependent correction term. And that's basically what the Hamiltonian is. And so I described a way of, for the example of graphene, of building a simple model with one phenomenological parameter. There may be cases, and there are cases, where you want more detail. Even for graphene, it turns out that this one parameter model has sort of 90% of the Moray physics, but there are small corrections. And in some other systems, it may be more difficult to build a model, a phenomenological model with just a small number of parameters. And if the number of parameters is not small, then the phenomenology is not useful, right? So, so you can also build a model in much the same velocity by simply calculating microscopically using tools of electronic structure, density functional theory, to calculate the full Hamiltonian projected onto a particular 2D momentum as a function of stacking and turning stacking into a function of position, as I described. This Hamiltonian can be expressed in a type binding representation using Wannier functions, for example, but it could be expressed in a plane wave representation also, and also re-expressed in terms of the representation of the eigenstates in the energy range of interest for some particular stacking. So you can calculate this local Hamiltonian in all its glory using much the same philosophy, without any approximations. And the parameters that appear in the Fourier expansion, assuming it can be truncated, you can just obtain by Fourier transforming with respect to stacking. Okay. Okay, so I've spent too much. When do I need to stop? I guess I didn't start at 9, right? 15, okay. Okay, so that example was graphene. One can hope in the fullness of time there will be many classes of 2D materials for which this Moray trick is useful for creating systems that have new types of physics or applications. But let me just talk about the next group, and this is as we'll hear in the tutorial tomorrow and in some of the research lectures. This is amazingly, I think this is pioneered by Phi. Is that right, Phi? The first experiment on TMDs, Mories, was yours. Is that right?
I would take the credit. No. It's fun one, I would say.
Okay. Very good. Okay. This is, anyway, a class that maybe it wasn't so obvious that everything would work so well for this system when experiments first started. But it's really been spectacular, the amount of physics that's been discovered in this TMD platform. So the TMDs, transition metal dichalcogenides, I've put up here the 5 transition metal dichalcogenides that have the 2H structure that I will talk about. These are group 6 transition metals. There are also transition metal dichalcogenides layered systems from group 4 transition metals. Those are also interesting but not much has been done with them experimentally. Our experimental colleagues maybe can tell us why. But let me start talking about this group. These are the electronic structure, energy versus momentum, of a single layer is what I showed you in the first slide. In a single layer, the top of the valence band is at the K point in the Brouin zone. And from these 5 materials, you can make, these, I guess, 15 different combinations and make moire patterns out of them. The ones in red here are homo bilayers. It turns out that when you make bilayers of the same material, in most cases, because the tunneling between the layers is much stronger at 0 momentum at the center of the Brouin zone, the gamma point, than it is at the Brouin zone corner, that level repulsion between layers in many cases moves the top of the valence band from the K point in the Brouin zone to the gamma point. And the exceptions are molybdenum ditelluride and tungsten diselenide. And so when these gamma moire systems and K moire systems are entirely different from each other in terms of their 2D Hamiltonians. You can also make hetero bilayers, and some of these hetero bilayers, the ones in yellow here that have a common chalcogeny, turns out the lattice constant in these systems is determined mainly by the size of the chalcogen atoms. So these have nearly the same lattice constant. So the moire periodicity is determined by twist angle. Here it's partly, for small twist angles, it's determined by the difference in lattice constant, and that's been an experimental advantage. So main point here, many of these materials, only some of them have been explored at this point. And maybe I have time to say this. I talked about gamma valleys moire systems and K valley moire systems. And there's there are many differences between them. Maybe the most important difference is there's only one center of the Brouin zone, but there are 2 inequivalent Brouin zone corner points, not related by reciprocal lattice vectors. So there are 2 valleys in K valley systems. And so that means that in this low energy world, valley becomes a label of the states, an internal label, much like spin. And there's getting mixed up here. There's a point about valley I want to make, and I realized at some point that it was first made a long, long time ago in a incorrect theory of superconductivity by these famous men. Actually, I must admit I can't read this, but the idea they had, the idea that they had was basically the observation that if you have block states that are close together, and they were thinking of 3-dimensional worlds, so close together in momentum space, because of the long range of the Coulomb interaction, states that are close together have very strong exchange interaction. The exchange interaction depends on the Fourier transform of the Coulomb interaction at the difference between the momentum involved. And they were, guessing at this time that this would tend to favor states in which electrons clump together in momentum space. And they imagined this tendency to get stuck together in momentum space would be strong enough to allow you to have a persistent current state, and that this could explain superconductivity. So we know it's not the correct theory of superconductivity, but it is a correct of something that is very common in all of these multi-valley moires, the tendency to form broken symmetry states in which the occupied one valley is occupied more than the other. Okay? It's really driven by exactly this thing that London and Heisenberg had in mind. And I won't have time to talk about this, but this is actually what's behind the quantum anomalous Hall effect that is common in graphene moires. And okay, so now I come back to the TMDs. Heterobilayers are very simple. As I showed you before, in a given valley, there's in this Moire world, we have different effective Hamiltonians for different valleys in general. For the K valleys, the two valleys are related by time reversal, so the two Hamiltonians are time reversed counterparts of each other. In the TMDs, it turns out that this structure has very strong, has broken inversion symmetry, and so there's spin degeneracy is lifted. There's only one state in a given valley at each momentum. And the Moire Hamiltonian in that case is very simple. So it's very simple to build a phenomenological model. The Hamiltonian, the local Hamiltonian, is what is the energy for this stacking, okay? So what you end up with in this case is just a quantum particle with a certain mass in a periodic potential, but critically importantly, in a periodic potential that has the Moire periodicity, as importance I explained before. And it turns out the scale of that potential is in the neighborhood of 100 millielectron volts, just a nice range that's big enough that you can tolerate quite a bit of disorder, but it's small enough compared to the atomic scales that all of this works. And so this system, quantum particle in a periodic potential, one type of quantum particle in a periodic potential, is almost perfect realization of a Hubbard model. And so these systems are really Hubbard model simulators. And unlike cold atom Hubbard models, there's an underlying lattice present in this system, so there's no problem, cooling the Hubbard model fermions to whatever temperature you like, to 100 millikelvin anyway. And you can vary the bandwidths in principle by varying the Moire pattern period, because if you have a given strength of potential, but you make the distance between extrema larger, than the tunneling from one minimum to another will get weaker and weaker. And it turns out that in this case, valley is locked to spin and it plays the role of spin. So these are really Hubbard model simulators, and we'll hear tomorrow that lots of Hubbard model type physics has been seen in these systems. And I have 5 minutes. Okay, so let me end with this one point, which leads to what is perhaps one of the most spectacular experimental results in this field so far that you'll hear about several times in this conference, and including in the tutorial tomorrow, is the fractional quantum anomalous Hall effect. I remember when the quantum Hall effect was first observed, and the fractional quantum Hall effect was first observed and misinterpreted as a Wigner crystal. And I can tell you from that perspective of 40 years ago, I could not imagine, that you could have. I could not ever imagine that a fractional quantum Hall state could occur without a magnetic field. And but now we have it. And so this occurs. This is the structure of the TMDs without inversion symmetry that I mentioned to you. This is from this very nice illustration I like very much. Comes from a nice review article by Phi and G, and it shows the local stacking of these TMDs So this is looking from the side, looking from above. The chalcogen atoms are above each other and on one honeycomb sublattice, and the metal atoms in the middle are on the other honeycomb sublattice. And so if you just change the stacking by basically moving the blue layer relative to the red layer, you can easily see that within each period of the Mories pattern, you find a point where the metal atom in the top layer, the blue layer, is on top of a chalcogen. So that favors holes to be in the top layer at this position, and if you move it the other way, then holes are favored to be in the bottom layer. Okay? So you're just looking at this, you can understand what the Hamiltonian looks like. The Hamiltonian is actually layer dependent, and the tunneling terms between layers are very similar to the ones I discussed in the graphene system. And what that means is if I look at the tunneling Hamiltonian and can think about layer degree of freedom as a spin-like degree of freedom, so a two-level system, but it's layer this time, then in these Mories, it turns out that in these chalcogen and metal on chalcogen positions, the tunneling between the layers in this local approximation vanishes at those positions. So the Hamiltonian is completely polarized to one layer at one point in each unit cell, completely polarized to the other layer at another point in the unit cell, and in between, the direction of the effective magnetic field described by the local layer-dependent Hamiltonian is an effective magnetic field that points in certain directions, and that object is topological. It its directions cover the unit sphere once in every unit cell. And so this is actually, in the case of magnetism, such magnetic structures for real spins are known. People refer to them as skyrmions, and if they're periodic, as skyrmion lattices. And as most of you know, skyrmion lattices are a subject in magnetism, in spintronics. But in those systems, there are hundreds or thousands of electrons per period of the skyrmion lattice, and the quantum effects get washed out. Here we have the sphere is covered, one skyrmion, the block sphere of this two-level system covered once in each unit cell. And that gives, this is the phenomenology. This is basically a phenomenological picture constructed in the way I was explaining for graphene. So there's something topological in real space, and that means if the Mories period is large enough, there's a Berry phase in real space that people have discussed in skyrmion lattices in spintronics. But it turns out that this Berry phase flux, Berry phase adiabatic concept, so this is for long period Mories, has one quantum, 2 pi phase Berry phase going around each unit cell. And so it looks very much like this Berry phase is very similar to an Aronoff-Bohm phase from a magnetic field, and it makes the system look like it's in a magnetic field, actually magnetic fields of opposite sign in the two valleys, even in the absence of a real magnetic field. And that's one way of understanding the established observation that these systems behave in many ways much like Landau levels, in the sense that there's a quantum Hall effect and also a fractional quantum Hall effect. And I think I'm out of time. I'll just leave it there. So, so this world, I think, it's just been amazing over the last 5 years as the techniques to control moire patterns have developed and new materials have been studied, and it seems like almost every time we look at a new type of moire material, we see new physics, and I'm very much hoping that this continues for a long time with new materials and new ways of stacking. So thanks very much.
Questions?
Any predictions of new materials?
Well, I'm playing around with a bunch of different things, but why don't people look at hafnium and zirconium dichalcogenides? They're in the conduction band. It should be easier to contact. The work function is the same as silicon, and and maybe it's terribly reactive. Okay, so that's a good reason. But
It's very reactive.
okay, so but techniques have improved, and the bottom, it's not a direct gap semiconductor, so some of the neat optical techniques won't work. But the interesting thing about it is that it's the minimum of the conduction point is at the M point in the Brouin zone. So it's a three-valley system, and there's been some crystal and topological insulators are supposed to have three-valley surfaces. So there's already a lot of theory speculation of what the properties of this type of system might be, and I think it'd be very interesting to study. There's a Muri call on oxide Mories. Whether they're really real or not, I'm not sure, but yeah, that would be cool.
Questions?
Actually, very, very naive question, but so I think you're using the hopping Hamiltonian. So could you write down the hopping coefficient analytically in terms of the twisted angle, and then you choose the magic angle so that the hopping coefficient is quenched? Is that how you find the magic angle, or is it just experimental?
Yeah, so I'm not sure if I understood your question. Was that a question about history or?
No, I mean, in theory, you can write down the hopping Hamiltonian, right?
Yeah.
And hopping coefficient depends on the angle of U twist or the periodic.
Not really. It's
not really.
What the phenomenological number that characterizes the strength of the hopping is independent of twist angle. What's changing with twist angle is the size of the momentum boost that you get when you tunnel to the other layer.
Oh.
So the Hamiltonian, there's one number so that matrix element that I showed you is independent of twist angle.
Oh. But then why is there magic angle which suddenly quench all the kinetic energy?
Well, that's something we can only answer approximately. There's a limit of this Hamiltonian where you have no tunneling from layer to layer, staying in the same sublattice. In that limit, you can show rigorously that there are a discrete set of twist angles where you have perfectly flat bands. So, this property was originally discovered numerically. That if you take this one parameter model, basically, twist angle being the second model, then you find that at certain discrete twist angles, the bands become very flat. And in terms of a simple theoretical understanding of that, you can say the system is close enough to this chiral model for this property to occur. But it occurs where the change in kinetic energy when you tunnel between layers and the tunneling have the same strength. So there's some kind of interference between hopping within a layer and hopping between layers that produces these flat bands at certain discrete twist angles.
Yes. Well, last question.
Allan. You mentioned that the method or the model wouldn't work if you have this constituents layers are metals.
Yeah.
So what happens if I have poor metals and
You mean
twist them?
poor conductivity?
Yeah.
Yeah,
Low
so-
density of states, some suppressed density of states.
I think the key thing is that all of the low energy states, and low energy, I didn't define those words. It means over an energy range that's comparable to the interlayer coupling terms in the Hamiltonian, or stacking dependence of the Hamiltonian. They have to be in a small region of momentum space that's doesn't change with stacking. So let's say for niobium diselenide, none of this works.
Okay, let's thank Allan again for the great talk. Our next speaker is King-Fai Mak from Cornell University, and he will discuss Moray semiconductors in connection with graphene.
Hello? Yeah, okay, cool, it works.